All right, here we go. We are going to try to code this Gaussian elimination. So we're going to do the forward elimination process and then also backward substitution. We don't need a lot of other plotting stuff that we've been using in the past. So all we need to really do is import NumPy, and we can just do a star import. We don't have to keep typing a bunch of things. The next thing we want to do is we're going to make a matrix that we can actually do something with. I mean, you could really pick any matrix that you want, but this is the one we'll choose. So this is it's a matrix that's representing a system of equations. -2, 2, 3. Next one, 2, 3. 3, 5, 8, 3. Nope, messed that up. 3, 8. All right. Now, something else we'll need to do in this particular case is we need to declare the data type for this matrix. Sometimes if you don't declare the data type, it may actually, since we've entered all integer values, when you go to do division or something like that, it might actually force it to do integer division unless we tell it to consider them float data types or some other type of data type that's not an integer. Okay. Now, since we're going to use the rows and columns numbers quite a few times in the algorithm here, we're actually going to code. We may want to get that ahead of time. That way we don't have to keep doing function calls for all of this stuff. So I'm going to use the shape function, and I'm just going to get the very first item from that tuple that shape returns, and I'm going to have another variable called calls. I'll use shape once again, and I'm going to pull out the second element in that tuple. So the shape function returns the rows is the very first element, and then the number of columns is the second element, right? And I mean, you could do it for any higher dimensional array-like objects if you want, right? So if you had like a tensor or something else, you could put it into shape and it would give you all of the requisite values that you'd want. Okay, now I'm going to call something else x. This is just going to be a vector of zeros, and the number I'm going to have is actually the number of columns minus 1. Why do I do that? Well, because I mean the matrix that we created initially is actually an augmented matrix, right? So if you think about the matrix equation, AX is equal to B, right? What I've done is I've taken the B vector and I've basically just joined it to the A matrix. So the X that I want, right, the X's actually have, it's actually 1 less than the number of columns I have here, right? So it should just be the number of columns in the matrix A, and in this case there would be 3, so that's what I want. But the number of columns I have stored here that I got from the shape function would actually give me 4. So this is what I want to do. Now for me, what I like to do kind of as I go along, I might actually want to just kind of print this out and make sure I'm on the right track, right? Periodically I like to check in with how my code is going and make sure I'm doing everything correctly. So if I just run print here, all it should return is the matrix for me. If it does, that's great. Yeah, so here we go. Note that even though as I entered whole numbers here, you see these little decimals, that just means it's storing them as a float data type, which is what I wanted. So there we go. All right, so now it's on to the forward elimination step. This is really not all that all that difficult. It just kind of sometimes is a little bit difficult to think through. But what we want is we want to kind of stair step down through the matrix, right? So imagine going left to right in the matrix, and then from top to bottom, right, to do the forward elimination. What I want to do is I want to have sort of a pivot, right? I want like a pivot element, and that's going to be in the it's going to be a row and column index. So if I start at the top, it's going to be my 1, 1 place, and then it's going to be the 2, 2 place, and then the 3, 3 place, and then so on and so on, right, as I stair step down. What I want to do is I want to eliminate all of the values in the column below that, right? And that's how we do forward elimination, right? So as we stair step through, right, I should eliminate everything in the first column below the 1, 1 value, and then I should eliminate everything in the second column below the 8, 2, 2 value, and then so on until I'm done. The nice thing about this is that it doesn't matter the size of the matrix I actually put in here. It should, like the algorithm itself, should handle it, so it doesn't really matter. So first off, what I want to think about is kind of moving left to right. This is how I think about it. I start sort of on the left, right, in the first column, right, and then once I have that first column element, right, I then want to go down that column, right? So going down the row. So then what I want to do is create another what's called a nested for loop, right? And here I'm just going to use J for my index numbers here. And I don't want to include my pivot element in here, right, when I'm running through here. So what I want to actually do is go from I plus 1 to the number of rows that I have. Right. Now, I'm going to type something out. It might look a little bit strange. I'll kind of explain what's happening here. So if you've taken a course in linear algebra, or you took a college algebra course or something like that, and you did Gaussian elimination, you know what you wanted to do is you wanted to store some multiple of whatever your row was, plus the row you kind of want to get rid of the element in. You want to put that back into that same row without changing the row at the top or the next one down or something. You only want to change that one. So here, what I'm saying is I want to store everything in whatever row J happens to be, right? So this is row J, all columns, right? So whatever I have, I want to store in there. And the way we're going to do this is just like this. So I have negative A. All right. So notice that this is the element, right? This should be the first element in row J. So, it's the row J column I element. Then I'm going to divide that by, right? This AII, this is really the pivot element I was talking about earlier. So I'm going to multiply all of this, right, by the ith row. Right. Then what I'm going to do is just add that, right, to this row J. Right. And that's it. That is forward elimination. And this algorithm here should take care of all of it. Now what we should get at the end, right, I can print A again. And what it's going to give me, hopefully, tons of times I make mistakes on stuff, so we have to go back and fix something, but I believe what it should be giving us is the row echelon form of the matrix, right? So that's where we have zeros in the lower half, right, of the matrix, and then we should have an upper triangular matrix for the rest of it. So if I run this, right, Notice I have the zeros in the lower half, and I've got an upper triangular matrix right here. So this is what I expect, right? Now, what do? Well, now we need to get to the back substitution algorithm. The way I like to think about this, right? If the forward elimination started from, left to right and then top to bottom, the back substitution is really going to kind of start the opposite way, right? So I kind of think from going bottom to top and then right to left, right? At least that's how I think about it. So I'm going to write out how I actually accomplish this. So I'm just going to have another index, A range. I want to go to rows -1, 2. Okay. So here I have another for loop. This is going to allow me to iterate through basically the rows. And the reason I'm doing this, I'm starting at rows -1 and going to -1. Well, because I have to think about the indices that I really want in this, right? So if you remember kind of how stuff is stored, I mean, if I have 3 rows in a matrix, and I have this number rows, the number of rows is going to be 3. But if I put 3 in here, that's actually going to be out of bounds, right? If I put in that index number, right? Because if you think about how it's stored 0, 1, 2 sequentially. So what I would need is actually to start at 2. So here I need rows -1, so that should start me at 2. And the arange function here in Python, it's very similar to the range function in that it starts wherever you tell it to start, and it goes up until basically you're less than that upper bound there. So if I put 0 here, right, this would only start at 2, and then it would go to 1, and then it actually would not include 0. So I need to include 0, so that's why I have to make it go from -1, and I actually want to be going down, right? So I want to start at 2, go up to 0. So this is going to let me do that. How am I going to do this? Well, what I want to do is I want to take, right, the element that I want here, right, and I'm storing stuff in my x vector now. What am I going to store? Well, here I have A, I. Now this is a shorthand for me to get the last column element, right? This -1 just allows me to pull the last element that's in the array here. Okay. Now I'm going to subtract A, I. I'm going to go from 0 equals -1. Right. I'm just going to do this x. So this looks like a lot going on here. There's a weird @ sign. This @ sign is allowing me to do some matrix multiplication. Why am I doing this? Well, because I find it to be actually the easiest thing. So here if I start at I, right, at row I, and I go from 0 to whatever, right, columns -1. So in this case it would be going from 0 to 2. I could multiply this, right, by this vector right here. And it should allow me to basically use matrix multiplication to my advantage to complete this algorithm. Now all that's left is me to divide by my A and I element. Right? So now I could print X, and we can see if we accomplished what we wanted. Here we go. So there's my original matrix, right? There's the row echelon form of the matrix, and here I have my solution vector printed. All right, there it is.